You know, everything you see, everything you touch, from a solid steel beam to a simple glass of water, it's all being governed by a hidden set of rules. So in this explainer, we're going to pull back the curtain and take a look at the invisible forces that decide the very state of matter itself. So what could a steel beam, a glass of water, and, well, the very air you're breathing right now possibly have in common? I mean, they seem like total opposites, right? But the answer, it's actually in a hidden battle, a constant push and pull happening between their tiniest particles. And if you stick around, you're going to see exactly how this invisible tug of war shapes pretty much our entire world. Okay, so here's our game plan. First, we'll cover the 3 basic states of matter. Then we'll dive into that push and pull that defines them. After that, we're going to decode the simple rules for gases, see how they all mash together into one universal equation. And finally, we'll look at what happens when these ideal gases get real. All right, let's dive right in. We're starting with the absolute fundamentals, the 3 states of matter that, we all interact with every single day. So pretty much everything around us exists in one of 3 physical states. You've got your solids, which have a fixed shape and volume. Think of a rock. Then you have liquids, which keep their volume, but, they'll take the shape of whatever container you put them in. And finally, there are gases, which have no fixed shape or volume. These 3 are the main characters in our story today. Okay, so the big question is, why? What actually makes something a solid, a liquid, or a gas? Well, it all comes down to this constant, invisible battle that's happening between 2 totally opposing forces. So, in one corner, you've got the pull. This is what we call intermolecular forces. It's like a kind of molecular superglue that's always trying to pull particles together. And in the other corner, you have the push. This is thermal energy, and its whole job is to make particles move, to jiggle, to vibrate, and just try to get away from each other. It is a constant, nonstop competition. And here's the kicker. The winner of this battle determines everything. If the pull wins, if those intermolecular forces are dominant, boom, you get a solid. If the push of thermal energy wins out, you get a gas. And what happens when it's a really close fight, almost a tie? Well, that's when you get a liquid. All right, let's zoom in and focus just on gases for a bit, because this is where things get really, really interesting. See, in a gas, the push has totally won the fight. The particles are just so far apart and they're moving so fast that the pull between them is practically zero. And this makes their behavior, well, surprisingly simple to predict. Okay, first up, we have something called Boyle's law. Just picture yourself squeezing a balloon, right? As you shrink the volume, literally giving the air less room to move, the pressure inside goes up. It has to. You've got more particles bumping into the walls in a smaller space. That relationship, one goes down, the other goes up, that's Boyle's law. Next on the list is Charles' law. And for this one, think about a hot air balloon. When you crank up the heat on the air inside, what happens? Those particles get a huge boost of thermal energy, way more push. So they start moving around like crazy and they expand, taking up way more volume. And that's what makes the balloon rise. So higher temperature means higher volume. Simple as that. And finally, we've got Avogadro's law. And honestly, this one is kind of mind-bending. It says that if you take 2 balloons that are the exact same size and you have them at the same temperature and pressure, but you fill one with super lightweight helium and the other with much heavier carbon dioxide, they will contain the exact same number of molecules. Isn't that wild? The type of gas doesn't matter at all. It's all about the space it takes up. So, okay, we've got these 3 different rules, right? Boyle's, Charles', Avogadro's. But here's the really powerful part. They don't just exist on their own, in isolation. We can actually weave them all together into one single, super powerful universal equation. So first, when you stick those laws together, you get what we call the combined gas law. And this thing is like a crystal ball for gases, seriously. It means that if you know the starting conditions of a gas, its pressure, volume, and temperature, you can predict exactly what's going to happen to the other variables if you decide to change just one of them. It's incredibly useful. And all of this leads us to one of the most famous and elegant equations in all of science, the ideal gas law. You've probably seen it before. PV equals nRT. This is basically the equation of state for any so-called ideal gas. It perfectly connects its pressure, its volume, and its temperature to the actual amount of gas you have. This isn't just some random formula. It is a true cornerstone of modern chemistry and physics. So let's just break that down really quick. P is for pressure, V is for volume. Easy enough? Now, N stands for the number of moles. Just think of it like a chemist's version of a dozen. It's just a way to count a massive number of molecules at once. T is the absolute temperature. And R? Well, R is the magic ingredient. It's the universal gas constant, a special number that just makes the whole equation work perfectly for any ideal gas anywhere in the entire universe. Okay, so we have this beautiful, perfect rule for ideal gases. But what about the real world? What happens when things aren't so ideal? What if you really crank up the pressure or drop the temperature way down? And those intermolecular forces, remember the pull, what happens when they start to matter again? Well, that is exactly how you turn a gas into a liquid. It's a two-step process. First, you ramp up the pressure. You squeeze those molecules closer and closer together. Then, step two, you lower the temperature, which basically steals their thermal energy. It takes away their push. And suddenly, the molecules are close enough and they're slow enough that their natural attraction, the pull, finally gets to take over. And just like that, the gas condenses into a liquid. And this reveals something really powerful, a whole new way to think about this. A liquid isn't some totally separate, mysterious state of matter. You can think of it as just a super, super dense gas. It's a state where the particles have been squished so close together that their pull becomes incredibly strong, and that's what holds them all together. So think about it. From the air pressure in a car tire, all the way to the weather patterns on Earth, and even the stars in the night sky, it all comes back to this one fundamental idea, this constant, invisible battle between push and pull. These laws don't just explain why your ice cube melts. They govern the formation of clouds, they explain how stars forge new elements, they literally dictate the rules for almost everything in the universe. So the next time you look up at the sky, or even just watch the steam rising from a kettle, remember what's really going on. You're watching the secret rules of matter play out right in front of your very eyes.